We've got new JWST exoplanet news. Oh! It's not the TRAPPIST-1 data that we've all been impatiently waiting for to see if they have those biosignatures in their atmospheres. But we have had the release of the most detailed spectrum of an exoplanet ever taken. So let's chat about what this data is, what it can tell us, and why do we care. So the object that's been observed is VHS 1256b, which is around 10 to 20 times heavier than Jupiter. And it's orbiting a binary system of stars. So not one star like the sun in the center of the solar system, but two stars in the middle of this star system. And it orbits those stars around about 150 times the Earth-Sun distance. Now to put that into context, that's about 4 times further out than Pluto orbits the sun, and it takes 10,000 years for it to complete one orbit.
10,000 years will give you such a crick in the neck.
Now the stars that it orbits are around about 40 light years away, and they're both the same kind of stars known as M dwarfs. They're actually only around about 64 times the mass of Jupiter each, or around about 6% of the sun's mass. So they're much smaller than the sun, and they're much cooler than the sun as well, at around about 2,600 Kelvin. The stars are actually so faint, they were only discovered in 2015 when Gauss and collaborators were searching for stars that wobble because they have planets orbiting them. And they were spotted in data from the Vista Hemisphere Survey, which is what gives the stars and the planet that VHS name. It's nothing to do with video home systems, unfortunately. So this system's a really interesting one because the stars in the center are the smallest stars that you can get, right on the edge of what you would classify as a star versus a failed star with no hydrogen fusion going on, known as brown dwarfs. And then you've got a planet right on the edge of the mass of a planet and the mass of a brown dwarf, which we think that threshold is around about 13 times the mass of Jupiter. The way you distinguish between planet, failed star, aka brown dwarf, and then the smallest of stars is that those brown dwarfs actually can have some deuterium fusion going on in them. So instead of hydrogen fusion into helium, taking deuterium, which is heavy hydrogen, and fusing that into a lighter helium. You don't quite need the same intense pressures and temperatures for deuterium fusion like you do with normal hydrogen fusion. So it's a really interesting object to study, VHS 1256b, so that we can better understand that boundary of when does a planet become so massive that it becomes a failed star. Hence why an object like this was always going to be chosen for JWST's early release science observations. So these are observations taken in the first 6 months of operation of JWST, and after very quick analysis are released to the public, essentially to show what JWST is capable of, especially so that other astronomers wanting to study brown dwarfs and very massive planets then have an idea of what they can do with the telescope. VHS 1256b was also chosen specifically because it orbits so far out from its star. So there's no contamination from the light of the star. You can observe this without doing anything fancy like using a coronagraph where you block out the light from the star completely, or where you wait for the planet to pass in front of the star to get what's known as the transmission spectrum, where starlight passes through the planet's atmosphere. Since it's so far away from very faint stars, you can just point the telescope straight at it and observe the light from it, just like you do with a planet in the solar system, for example. Another reason why it was chosen is because it's also the most variable planetary mass / brown dwarf object that we know of, with Zhu and collaborators in 2022 finding that its brightness is so variable that it changed by 38% in just 2 years. That suggests that this object has a very turbulent atmosphere, with storms and clouds, the likes of which that we see on Jupiter or Saturn, causing a change in how much light that object reflects back, so starlight that's reflected off it, or how much of the infrared light interior to the planet, because it is so hot and dense in there, actually escapes through the atmosphere. So the plan was to test what JWST was capable of and observe it with both NIRSpec, JWST's main spectroscopic instrument on board, in shorter near-infrared wavelengths, and with JWST's MIRI instrument at longer mid-infrared wavelengths. Both of these instruments take the light from an object, split it through a prism into the object's component wavelengths, and make a trace of how much light at each wavelength you receive. And by doing that, you can get the most detailed spectrum over the largest wavelength range we've ever taken of an exoplanet, a planet in orbit around another star. And it really is just a thing of beauty. Like, the detail is just absurd. People in the exoplanets research field are just absolutely raving about this spectrum. And all of these lumps and bumps in the spectrum are fingerprints of molecules in the atmosphere of this planet that have absorbed or stolen away a bit of light at a given wavelength. So once you have this full spectrum of the light that you're receiving from the planet or an object, what you can then do is sort of build up like a recipe for what the atmosphere is made of. So what combination of these elements and these molecules all absorbing light at these different wavelengths give you what you observe. So, a little bit of carbon dioxide, a little bit of water vapor, a little bit of methane maybe as well. So you can see that here in the yellow line in this plot. This is like sort of the fingerprint of methane, how much light it absorbs at each wavelength, which is plotted along the x-axis there. Then in the black line, you can see the data that's been recorded by JWST for VHS 1256b. And you can see those same absorption features that methane is responsible for imprinted on the light that you receive from this planet amongst all of the noise in the data. The most exciting feature, though, is the detection of silicates in the spectrum. So molecules with silicon and oxygen in them, which could be so small that they'd resemble, just like smoke particles, or just that little bit larger so that they'd resemble more like sand or dust here on Earth. Which is why I've seen a lot of comparisons of this planet to Tatooine in Star Wars. It's very sandy. It orbits 2 stars. But Tatooine is supposedly an Earth-sized planet, whereas VHS 1256b is anything but. It's so big it might not even be a planet anymore. But this silicate detection means it's very likely VHS 1256b does have these big, dusty clouds, storms maybe, covering the planet, explaining the variability that was seen previously by Zhu and collaborators. Now, the paper that's been published this month by Miles and collaborators that made this spectrum public is just a preliminary study, sort of like a first look at what JWST found, because this spectrum is so detailed that there's going to be so much more that we're able to pick out of it. And I think one thing that the JWST early release science team will be doing, or any astronomers studying planets and brown dwarfs and that line between them, is looking for deuterium, or molecules that contain deuterium in the atmosphere of the planet, and see if they can spot those fingerprints that give away that they're there. Because once you cross that threshold at 13 times the mass of Jupiter-ish, from planet to brown dwarf, aka failed star, you start fusing deuterium into light helium. And what that means is that the ratio of deuterium to hydrogen in the atmosphere starts to drop as you start turning that deuterium into something else. And so by trying to work out, okay, do we have molecules of deuterium in the atmosphere? How much of it do we have? How does that compare to how much hydrogen you have? You can actually start to pinpoint, okay, where is that threshold? 13 times the mass of Jupiter is just the current estimate that we have, but how precise is that? Does it move around a little bit depending on the conditions you have or the properties of the planet? This was something that was actually investigated by Morley and collaborators in 2019, who predicted you should be able to see these deuterium features with JWST. So I'm going to be on the lookout for studies that are published trying to do just that with this data that's just been published on VHS 1256b. So make sure you're subscribed so that you never miss a video. If you want to hear more from the lead author on this paper, Miles, I'll link an interview they did with the SETI Institute in the video description down below, where they talk about what they found and what they think's next with JWST. Because with everything we've seen so far from JWST in just its first 9 months of observations, right? There's not even been that much time for all of the projects that have had proposed for data to actually analyze it and publish it yet. Even with everything we've seen so far, there is no doubt that JWST is going to revolutionize every single area of astrophysics. And I, for one, cannot wait. Which, to put that into context, that's 4 times further out than the Pluto. The Pluto. Hi, Pluto! And it takes 10,000 years for it to complete one orbit. 10,000 years gives you such a crick in the neck. Tatooine. Have I remembered that rightly? Tatooine. There's only so many times you can say Tatooine before you just start doubting that it even exists as a word. Oh, the rain is so heavy outside. I really hope this doesn't come across on the microphone. It's like hailing. Like, the sound of it hitting the window is insane right now. This is why I don't leave the house. The planet is super dusty and I'm gonna get squished.